Welcome to The Explainer. Today we're unpacking one of the absolute most fascinating and, let's be honest, notoriously tricky challenges in modern system design. We're talking about the hidden complexities of querying distributed databases by non-primary fields. Seriously, if you've ever wondered how massive web-scale applications let you instantly filter millions of items without bringing the entire system crashing down, well, you're in exactly the right place.
Okay, let's just dive right into our agenda. We'll start with our partitioning baseline, introduce the secondary index problem, and then explore local indexes and the scatter-gather-read penalty. Finally, we'll look at global indexes and weigh the ultimate distributed trade-off. Let's get into it.
Section 1. The partitioning baseline. Let's quickly set up the foundation using a real-world e-commerce catalog case study. Just imagine you're building the backend for a massive online retailer, storing millions and millions of products.
Right, so when you partition, or shard, a database, your main goal is to spread the data and the query load evenly across multiple machines. Now, when you're accessing a record by its primary key, like a unique product ID, this process is incredibly straightforward. I mean, it's pretty much the absolute ideal scenario for a distributed system.
Here's a quick look at a day in the life of a primary key lookup. The client requests product ID 867. The system runs that ID through a hash function, which instantly tells the network, okay, product 867 lives over on partition A. The request routes directly to partition A, grabs the data, and returns it. It's completely effortless because the network routing knows exactly which node holds the data. No guesswork, no wasted effort whatsoever.
Section 2. The secondary index problem. So here's our inciting incident. Our e-commerce app is scaling rapidly, and suddenly we've hit a massive roadblock. See, the primary key lookup is fantastic for the backend, but it completely ignores how humans actually behave. Which brings us to this really critical question. How do we actually query data by fields other than the primary key? I mean, think about your own habits when you're shopping online. You almost never go to a search bar and type in some random 16-digit alphanumeric database ID, right?
No. Instead, you search using specific filters. You want to see shoes by a certain brand, maybe within a specific price range with a 4-star rating that are currently in stock. These user-friendly filters do not map neatly to our primary key partitions at all. And if we just blindly search for them, we'd literally have to scan every single document in the entire database.
And this brilliantly illustrates why we need what engineers call a secondary index. Basically, it's an additional data structure maintained alongside your primary data. It acts kind of like a signpost to help you efficiently locate records based on those non-primary key values. Now, in a traditional single-node relational database, secondary indexes are the bread and butter. You just declare them and move on with your life. But in a distributed system, oh boy, they introduce some serious complexity. Because suddenly, this index doesn't map cleanly to your partitions anymore.
Section 3. Local indexes, which is also known as document partitioning. Let's see how we can actually try to solve this.
I want you to think of this approach like a series of physical filing cabinets. Each cabinet represents a partition on a different server. In a local index, every single cabinet has its own independent mini-index inside it that only tracks the files in that specific cabinet. It doesn't know, or frankly care, about what's stored in the other cabinets across the room.
Now, the major advantage here is super clear. When a supplier adds a new pair of sneakers to our catalog, the database only needs to talk to the specific partition where that new document is being saved. It writes the primary data, updates the local secondary index right there on the exact same machine, and boom, it's done. Writes are delightfully simple, they're fast, and they're completely localized.
Section 4. The scatter-gather-read penalty. Because, as you'll soon learn in system design, there is absolutely no free lunch.
Okay, so writes are incredibly easy now. But what happens on the read path? What actually happens when a user opens the app and hits that search button? Well, this is exactly where the complications of local indexes rear their ugly head.
Let's ground this technical architecture in a very specific, tangible user experience. The user submits a query, find all shoes under $100. Now remember, our database is partitioned by something like product ID, not by category or price, and our indexes are completely local to each partition. Because we have absolutely no idea which partitions contain these affordable shoes, we're forced to execute what's called a scatter-gather process. Step 1. The system scatters, broadcasting the query to every single partition in the whole cluster. Step 2. Each partition individually searches its own local index, And finally, step 3, the system gathers all the individual results, combines them, and sorts them to show to the user. Asking every single partition to check for shoes is computationally really expensive. And worse, it's highly prone to what we call tail latency amplification. Think about it. If just one partition is running slow because of a random network hiccup, the entire user search is delayed, just waiting for it to respond.
So the crucial point here is this classic seesaw effect. Local indexes give you fast, isolated writes, but they punish you with slow, expensive, scatter-gather reads. A lot of popular databases, like MongoDB, Cassandra, and Elasticsearch, actually use this approach because of how well it scales for writes, but it absolutely requires developers to be very, very careful about how they route their read queries.
Section 5, Global Indexes or Term Partitioning. Now, if scatter-gather is just way too slow for your application's read workload, we need to shift gears to this architecture, which is designed specifically to fix that painful read path we just described.
So, instead of having isolated mini-indexes in every cabinet, imagine we build a massive master index cabinet for the entire room. A global index covers data from all partitions, but it's partitioned separately by the search term itself. So for example, all index entries for the color red might be grouped together on node 1, while index entries for the brand Nike might be grouped on node 2, and that's regardless of where the actual product details actually live.
Let's see how this builds a better user experience. When a client makes a query, say filtering products by a specific brand, the routing is suddenly lightning fast. We don't have to scatter-gather anymore. The system hashes the term, knows exactly which single partition holds the global index for that brand, and routes the request directly there. It's a real game changer for reads.
But remember the seesaw. If global indexes make our reads incredibly fast and efficient, what is the heavy toll we have to pay on the flip side? This right here is the eternal back-end struggle.
The reality is, writing data becomes extraordinarily complex. If you update a single product document, let's say you change a shoe's price, color, and availability, you might have to update 3 entirely separate term indexes located on 3 entirely different network nodes. Doing this safely requires distributed transactions, which can literally stall the entire system. Because of this massive penalty, many databases, like Amazon DynamoDB, are forced to update global secondary indexes asynchronously. You write your product update, it returns success, but there might be a fraction of a second, or maybe even longer during a fault, before that product actually shows up in the user's search results.
Section 6, the distributed trade-off. Which brings our explainer to its synthesis and conclusion. Because every tool you use to scale data ultimately forces you into a corner where you just have to make a choice.
Let's draw the ultimate comparison here. Secondary indexes grant us the immense query flexibility that modern users expect and demand, but they enforce severe routing and consistency trade-offs. If you choose document partitioning, you get robust, fast writes, but you must suffer through scatter-gather slow reads. If you choose term partitioning, you unlock lightning-fast reads, but your writes become complex, slow, and often just eventually consistent.
So, I want to leave you with this to ponder as you architect your next application. In a massively distributed world, where every millisecond of search latency costs you money, are you willing to sacrifice immediate consistency to give your users a lightning-fast experience? There's no single right answer, only the right trade-off for your specific workload. Thanks for joining me on this explainer, and keep building great systems.